start on the last chapter of this class, chapter 8. In this chapter, we're going to talk about energy, to be more specific, electric energy from chemical reactions. And the title is Energy from Electron Transfer. Okay, the title seems fancy. It's energy from electron transfer. Basically, this topic is involving something we use every day, a lot every day. Even nowadays, you guys are using laptops, you're using something called energy from the electron transfer, and that is battery. Okay, we're using many types of batteries in our daily lives, and this is a picture of the Tesla battery pack, the Powerwall. I don't know if you guys heard of it. Tesla is not a company that only make electric cars. They're also focusing on batteries, and hopefully one day we can see that our daily life is not powered by power companies. We actually have battery storage, large battery walls in our house. Of course, they're chargeable batteries, maybe from solar light, and then we can have sustainable using your batteries. But in this chapter, we're going to talk about these topics. Okay, what are the main batteries and how do they work? And what is the difference between these two types of batteries? One is called a galvanic battery, which is our focus of this chapter, and also we'll briefly talk about electrolytic cells. And then we will also discuss how batteries, different types of batteries are recycled, what are recyclable, what are not recycled, and what are electric vehicles and also hybrid vehicles, and also any benefits of using a very unique type of battery called fuel cells instead of gasoline-fueled vehicles. So we're going to talk all types of batteries, and especially how do they work, and what are the futures and what are the directions of battery industry and battery development. Okay, first, let's take a look at the basics of energy from electron transfer, called battery. Okay, and a battery is a term describing a system that convert chemical energy to electric energy. So even we say battery every day, but this is the definition of battery. Something that as long as they can convert chemical reactions or energy from chemical reaction into electricity, then that device is called a battery. Okay, and during our daily life, the battery is actually a broad concept. For example, this is a battery pack of a nickel cadmium battery. Okay, if you guys use sometimes the small power tools, okay, those are nickel cadmium battery. A battery like this is actually a system. It contains of small units. Okay, those small units are called galvanic cells or voltaic cells. Okay, mostly I call it voltaic cells. And these voltaic cells that are wired together constitutes a true battery. So a lot of batteries we're using daily are actually a wired pack of these basic unit cells. Okay, so what do you say what's the basic unit for batteries? Voltaic cells. Okay, some batteries, they constitute one single cell. But most batteries we use, like these ones, are actually wired together. These cells wired together. We call them what? We call them batteries. So in order to study battery and how they work, we first need to take a look, what is the basic principle of a voltaic cell? And how does a voltaic cell, this single unit, converts chemical energy into electricity? How electric energy is produced? So with that, let's take a look a lab scale or lab model of the voltaic cell or galvanic cell. Again, I call it voltaic cell most of the time. Okay, again, voltaic cell is the basic unit that does battery. Basic has all the ability of a battery, but it's a small unit that converts chemical reaction energy into electricity. And the chemical reaction that creates electricity is called a spontaneous chemical reaction. Spontaneous means the reaction will happen without any external driving force. Once you connect all the parts, the reaction will happen without any external driving force. And that reaction, when it happens, it will create electricity. But if you ask, what is electricity? Okay, I don't know how you guys studied physics. The electricity is the movement of what? The movement of charge. Okay, the definition of electricity is the movement of positive charge. But in real life, positive charge doesn't actually move. What moves is the movement of what? Electrons. Think about chemistry is the movement of what? Electrons. So what happened when electricity is created is you create a flow of electrons. Of course, the direction of electron flow and the positive charge flow is opposite. So when you talk about the direction of electric current will be opposite to the direction of electron flow. But again, it's the same thing. When there is a flow of electrons, you have electricity. Now, how do we have a flow of electrons in a chemical reaction? When two substances react, if they can transfer electron from one to another, then we achieve what? The flow of electrons. For example, in this lab scale voltaic cell, the transfer electron is actually happening from zinc metal to copper metal. And because of the transfer of electron, we have what? We have electricity. We have electricity. Now, when we talk about the word transfer of electron, it actually involves two sub-steps. What is transfer? Transfer means what? Somebody gives and somebody what? Takes. So you're actually talking about two separate processes if you want to achieve the transfer of electron between zinc and copper in this lab scale voltaic cell. So the transfer of electron is separated into two small steps, and those two small steps we call them half reactions. Why half? Because both together achieve what? The transfer. Okay, a transfer. So if you take a look at this lab scale voltaic fast cell, in order to achieve the transfer of electron from zinc to copper, zinc metal has to lose electron to give electron. Zinc metal normally gives 2 electrons to become what? Zinc 2 plus. If you remember chapter 5, we talk about the charge for zinc is actually what? Actually 2 plus. So zinc metal normally loses 2 electrons to become zinc 2 plus. Of course, the zinc 2 plus will fall into the solution of zinc sulfate. This process, zinc lose the electron, you see, lose the electron to become zinc 2 plus. We call this process or this half reaction oxidation. Okay, very important. Losing electron, we call that what? Oxidation. On the other hand, when the electron is lost, the electron again will flow to where? To the copper. At the copper site, the copper 2 plus in the solution will take those 2 electrons to become what? Copper metal. So copper 2 plus, take a look, receive 2 electrons, copper 2 plus becomes what? Neutral copper metal. Of course, the copper metal will be deposited on this copper rod. And we call this half reaction reduction. So a transfer of electron is actually the combination of oxidation and what? Reduction. Whoever loses electron is called oxidation. Whoever gains the electron will call what? Reduction. These two processes, half reaction, must happen simultaneously. Means what? Together. There's no way you can have one without another. Because one thing loses electron, there must be something to accept it. Okay, to accept. That's the basic principle of voting cells. Okay, voting cells. So if we write down the half reactions, it's like here. The oxidation, again, is what? Zinc lose electron to become what? Zinc 2 plus. Okay, lose negative charge, you get a positive charge. And the reduction half reaction is copper 2 plus in the solution gains these 2 electrons to become what? Copper. And we call this reduction. You can see that they're losing electron. Those 2 electrons are from here, gained by copper 2 plus to give copper. Okay, to give copper. If you add these 2 half together, again, we have seen this process many times before. When you add reactions together, basically what you do is what? Add everything from the left side of the arrow together and everything from the right side of the arrow together. You get the overall cell reaction. Now let me ask you, why in the overall reaction you don't see any electrons? Why electrons is not here? We have electrons, right? Why electrons are gone? When we add them together to give you the overall. What happened? When you add them together, electrons are both on what? On the left side of the arrow and also what? On the right side of the arrow. So we cancel the electrons on both sides. This is what we got. That's why in the overall reaction, you don't see the electrons, but you know the electrons are actually what? Transferred. From where to where? From zinc to where? To copper. You can see that zinc becomes what? Zinc 2 plus. Oxidation. Copper 2 plus becomes what? Copper. Reduction. There is a transfer, it's just the electron doesn't show anymore because this is the overall cell reaction. And we call the reaction like this a redox reaction. Redox is like a synthesized word. It's a combination of what? Reduction and what? Oxidation. That's what we call a redox reaction. Does it make sense? Again, this is what? This is the basics of Voltaic cell, or basics of a battery. The transfer of electron between what? Between 2 substances. Okay, this thing happening simultaneously. Okay, if you put them together, the reaction will go on without any driving force. Okay, again, make sure you know the terms. Okay, here is a link. Okay, here's the link showing you, you can study and play with the link, watch some more readings, showing you the process of the Statue of Liberty turns green. Okay, this process is actually also a redox reaction. What happened is copper is being oxidized. Okay, copper is oxidized and oxygen is actually being reduced. Okay, the green stuff is copper oxide deposited on the surface of the Statue of Liberty. Okay, again, the link is here. You can click and take a look what is going on during the process of Statue of Liberty turning green, and apply what we learned about the oxidation and reduction into this process. Again, link is here. All right, so a quick concept check for you guys. Okay, take a look at these 5 half reactions. Can you quickly tell what are oxidations and what are reductions based on what we just said?
A would be a reduction because you're adding
electrons. A reduction. Great, yes. B is?
Let's see. Would be oxidation.
B is oxidation because zinc what? Lose electron to become what? Zinc 2 plus. Very good. The third reaction?
Reduction.
Reduction because what? Gaining electron. You can see the charge from 7 becomes what? 4. That means you gain what? 3 electrons.
Mm-hmm.
Okay, the fourth one?
Oxidation.
Oxidation because what?
Losing.
Losing electron. Okay, losing electron. The last one? reduction, because hydrogen plus what? Gain electron. Okay, this is how you very quickly grasp the idea about the oxidation and reduction. Okay, these are all half reaction because what? You see the electrons are showing up in this process. That's why there are only half reactions. All right, now let's take a look at the battery we've seen at the very first of this class, the nickel-cadmium battery. Okay, you will call it the NiCad battery. Like I said, the NiCad battery are actually 6 nickel-cadmium cells. This is one of the cells wired up together to give you a battery, like in your small power tool. Okay, in this battery, in this cell, the same. There is a transfer of electron, but in this particular cell, the transfer of electron is between these two metals, nickel and what? Cadmium. And the directions of electron transfer between nickel and cadmium is from cadmium metal to nickel. Okay, from cadmium to nickel. This is the anatomy of this battery. You can see that the cadmium of the metal and also the nickel metal, they're actually separated by these sheets of potassium hydroxide. Okay, you can see that the yellow ones are the separators. Okay, why do we have to separate these two? Because we don't want them transfer what? In contact. We want them transfer from where? From the external circuit. Why? Because we want what? We want to utilize the what? The electricity. We don't want the reaction happen like in the flask. We don't want them in contact with each other. We want the transfer not directly between them. We want to transfer what? All the way through a what? A wire. Okay, which we're going to see in a few minutes as well. Okay, but let's take a look at the reaction of a nickel-cadmium cell. The oxidation reaction again is the cadmium, which loses 2 electrons. So cadmium metal becomes cadmium 2+. And we call this again what? Oxidation. On the other hand, nickel does not exist in the battery as nickel metal. Nickel exists in the battery as nickel 3+. And during oxidation, nickel turns into nickel 2+. Think about it. From 3+ to 2+, how many electrons is gained? 1, right? But cadmium loses how many? 2. So in order to gain both the electron from cadmium, you need 2 nickel 3+ to gain those. That's why you see we have a 2 in front of these things. Okay, 2 and 3. And after that, you have 2 half reactions, oxidation, reduction. You add them together, electrons are canceled. This is the overall reaction of nickel-cadmium cell. Nickel loses 2 electrons to become what? Nickel 2+. We call that oxidation. I'm sorry, cadmium loses 2 electrons to become cadmium plus. We call that oxidation. Nickel 3+ becomes what? Nickel 2+. And you need 2 of them because what? You need the total number of electrons transferred equal to 2. Okay, equal to 2. So that's what happened in a nickel-cadmium cell. Okay, this is the simplified version. Later on, we're going to take a look at what's really the substances are inside the nickel-cadmium cell. Right? So here are some like a mnemonics help you to memorize the terms of redox. Okay, redox. Oxidation is what? Losing of electron. Reduction is what? Gain of electrons. So one way to memorize is oil rig. Oxidation is loss. Reduction is what? Gain. Gain of what? Electrons. Or in another way, okay, loss of electron is oxidation. Gain of electron is what? Reduction. So you take the first letters, you get a Leo. The line says ger. Okay, Leo the line, Leo ger or whatever. Okay, I don't use those, but it may help you guys to remember these terms. It's very important. You have to define. Okay, and those are some links to show you some more info about redox. Okay. Now, like we showed nickel already, nickel is actually changing from 3 plus to 2 plus. Okay, that's very common in redox reaction because we know different elements, they can have different charges. So different elements, depends on their group number, they will have different, now we call them oxidation states. Okay, oxidation states, basically, they have a preference of gaining or losing different number of electrons. Okay, you can see the main group element, like group 1, group 2, group 3, group 4, group 3, they mainly losing 1, 2, or 3 electrons. Okay, the nonmetals will gain electrons which is similar to their charge or the same to the charge. But for these transition metals, you can see their oxidation state can be various. Okay, depends on what reaction we're talking about. Okay, that's very common for redox. And to reinforce the concept of oxidation states, okay, oxidation states, your lab, I think the last one in this class is talking about redox reactions. Okay, after you study the lab, you have a better idea about what is called oxidation states. Okay, in this class, we're not going deeper into oxidation states, right? Now, like we stated earlier, in the nickel-cadmium voltage cell, okay, this is the anatomy of the cell again, we have cadmium and nickel 3+. Okay, in this case, nickel is 3+ charge. They're not in close contact together. Meaning what? Even though they're transfer electron, they're not transfer what? Direct contact. If you're transfer direct contact, you're not creating electricity. You're just doing what? A redox reaction. But because they're separated by the separator, potassium hydroxide, this plate, this paste, so the transfer electron has to what? Has to go from what? From outside. From one side of the battery to another side of the battery. So the electrons will move across the whole external circuit. And that movement of electron from outside will create what? Will create electricity for us to use. Now, the electricity or the electrons will always flow from the cadmium, which loses the electron, to what? To nickel. It means the cadmium has higher electron potential. That would guarantee electron always flow from where? From cadmium to what? To nickel. Just like your water, moving from higher end to lower end, because what? The water in the higher place has higher what? Potential. Will always flow from higher to low. The same, electrons always from higher to low. And that potential difference is called the voltage of the cell. You guys have heard of voltage, right? The different battery have different voltages. What is voltage? Voltage is the potential difference between these two substances. Okay, these two substances. Does it make sense? Now, next. Okay, we have many new terms you have never heard of before in this chapter. Another different terms, very important terms, are electrodes of a battery or of a cell. In order for a reaction to happen, in order to a transfer of electron to be possible, okay, the chemicals during a voltage cell are actually placed on a conductor. Okay, placed on a conductor inside a cell. And the conductors are the sites for the half reactions. What are sites? Means where the reaction are actually happening. These chemicals has to be placed on the conductors. And those conductors are called electrodes. Okay, called electrodes. Now, because we have two half reactions. One half reaction, like here, cadmium, again, what happened to cadmium? Losing electron, is that right? When cadmium losing electron, we call the reaction what? Oxidation. So the electrode where oxidation happens, or we say the electrode where losing electron happens is called the anode of the cell. Nickel is where electron is what? Gained. That's where reduction happens. We call the electrode cathode. Okay, electrode cathode. And again, the electron flow is always from where to where? Anode to cathode. Why? Because anode losing electron, cathode gains electron. So electron flow in a cell is always from anode to cathode. And the difference between the potential is called, again, what? The voltage. Okay, anode has what? Higher voltage, higher potential. Why? Because the electron is going from here to where? To there. Again, just like water, going from higher place like a waterfall, from higher place to lower place. Okay, electron is higher on here. Electron is lower in there. That's why electron can always go from anode to where? To cathode. And the difference of potential is called the voltage. Does it make sense? Okay, now a few things about voltage. Okay, some common mistakes about voltage or common confusion about voltage. First, voltage, again, is the potential difference. This potential difference is solely dependent on the chemical composition of the anode and cathode. The chemical composition. What does it mean? It doesn't mean it is not dependent on how much the chemicals are in the cell. In another word, the voltage is not a function of the size of the cell. Larger cells contain more materials, so they can last longer. But if you have the same chemical composition, then larger cell will have the same voltage of a small cell. Does it make sense? Because the composition determines what? Determines voltage, not the amount. Very good example here is the battery you use every day at home. The dry batteries, you call dry batteries. You know the dry battery come with different sizes, right? AA, AAA, even they have quadruple A, and D size or C size. They're all the same type. Okay, alkaline batteries we call. But apparently D size is what? It's much bigger. Okay, it's like this big. Okay, very heavy D size. But the tiny AAA battery and the D size battery, they have the same what? Voltage. Our alkaline battery voltage is actually 1.5 volt. Larger D size basically means what? It lasts longer. Okay, it only lasts longer. But the voltage is the same. Again, voltage is not a function of the size of the battery, but the chemical composition. Okay, the chemical composition of a AAA battery and a D size battery are the same. They're both alkaline batteries, most cases. Okay, so let's finally review using this battery I've seen before. The first battery I've seen, actually, the lab scale battery, to review the terms and also show you what's going on in the real picture, what's going on in a voltaic cell. Okay, even though it's a lab scale, but the real life battery, they're the same principle. Okay, let's take a look at this cell. It has two electrodes. The left electrodes is the zinc metal. See that? It's a conductor. So the zinc metal is one of the electrodes. The other electrode is the copper metal. Okay, it's the copper metal. And we know between zinc and copper, zinc will lose the electron to become what? Zinc 2+. And we call this reaction oxidation. And where oxidation happens, this electrode is called what? The anode of the battery. And when the electron is lost, where does the electron go? It goes from the outside wire. If you have a light bulb here, it will light up now. And then go all the way to where? To copper. At the copper site, you can see these are electrons. the copper 2 plus in the solution will gain those 2 electrons to what? To become copper. And where did that copper go? Deposited on the surface of the copper rod. And we call here what? Reduction. And we call this electrode the cathode. Okay, the cathode. And so we know zinc is losing electrons to become what? Zinc 2 plus. You can see that zinc metal will become what? Less and less. But copper 2 plus gain electron to become copper. You can see the copper electrode is getting what? Bigger and bigger. Okay, this is what happened in the battery. Of course, these two beakers will be connected by a salt bridge to balance the charge. Okay, to balance charge. And briefly, how do we mean balance the charge? With zinc becomes zinc 2 plus, means you have more what? Positive charge in here. So the salt chloride will get into the beaker to balance the charge. The same, when copper 2 plus becomes copper, you're losing positive charge. So the sodium plus will get into the beaker to balance what? The losing of the positive charge from copper. So the salt bridge is basically bridging what? Complete the circuit. Okay, complete the circuit of voltaic cell. Does it make sense? Again, you have to memorize and understand the whole scheme of a voltaic cell, especially all the terms about the half reactions and the overall reaction and what the electrons are called and what's happening at each electrode. Okay, all the details about the terminology of voltaic cells. Okay, after that, let's take a look at our common galvanic cells we're using daily. Okay, of course, we don't use the one in the lab, but these are the one we use a lot. These are the most one you will use, actually, in our daily lives. Okay, we don't use like millions of types of batteries. We're using a few types, in fact. Okay, this table summarizes all these common types of voltaic cells, or the batteries. Nickel-cadmium battery, we just saw that. They're used in toys, portable electronics, digital cameras, and power tools, like I said. Okay, you can even see that what it says on the battery label. It says what type of battery. Okay. And now, many devices, okay, especially digital cameras and portable electronic devices, many times the nickel-cadmium battery is now replaced with this newer type called a nickel metal hydride battery. Okay, the voltage are very similar, 1.25 volt. Okay, again, these are cells. Okay, they can wire together to increase the voltage of the whole battery. Okay, both of these are rechargeable. Okay, next type, alkaline battery, is the one we use the most time. The dry battery at home, right? The one you buy from the Energizer or what's that called? The brand? Energizer. What's the other brand?
Duracell.
Duracell. Yes, Duracell. Those are the dry batteries. Okay, including AAA, AA, C, and D. They're in flashlights, small appliances, calculators, remote controls, toys, etc. Okay, they're 1.5 volt and they're not chargeable. Next, we have two lithium type of battery, especially this type, lithium-ion battery and lithium polymer battery. Okay, they're the ones in our cell phones, iPads, electronics, your laptops. Okay, most times they are lithium-based battery, either lithium-ion or lithium polymer battery. And finally, this type is also very commonly used, whether you realize it or not, lead acid battery. Where is that lead acid battery located? In your cars, right? The big battery block is actually 6 lithium acid cells together. Okay, that's why our car battery, the voltage is what? 12 volt. Okay, each one is actually 2 volt. 6 of them is 12 volt. Okay, and these two types are rechargeable. Okay, rechargeable. Okay, another type here I didn't mention too much is the lithium battery. Okay, lithium batteries are this tiny, mostly like a tiny bottom type of batteries. Okay, Okay, lithium battery. They're mainly used in alarms, watches, vehicle remote key fobs. So this is like a, the button, the small button type battery. They're mostly lithium batteries. They're not rechargeable. Okay, so those are the main types of batteries we're using, and we're going to take a look at most of them and how do they work. Okay, one of them I've taken already is lithium nickel cadmium battery, but we'll see their full scheme as well. So the first one is alkaline battery or dry battery. Okay, and we're going to explain how they work and also showing all the reactions and also showing why they're called alkaline, for example. Okay, this is the anatomy of an alkaline battery. The anode, again, what is anode, guys? Now we say these terms, you have to reflect what's the anode. Anode is what? Oxidation happens. Losing electron is what? Is the zinc plate wrapped up on the battery. If you peel off the label or the plastic wrap of battery, you will see this shining silverish metal wrapping up the battery. That is actually the what? The anode of the battery. Okay, mostly is zinc. What happened is the zinc losing electron becomes zinc hydroxide. Why they have zinc hydroxide? Because inside the battery, inside the cell, there is a paste of potassium hydroxide. A lot of OH minus is inside the battery. So when zinc lose electron, zinc will combine with the hydroxide right away to become what? Zinc hydroxide. And because of the paste of potassium hydroxide, we know potassium hydroxide is what? Is a base. The battery is called alkaline battery. The name alkaline means what? Means basic. Okay, means basic. On the other hand, the anode is zinc. On the other hand, the cathode is at the center of the battery is a rod of graphite. Okay, graphite is not the chemical that involved in the reaction. Graphite is basically the conductor, like we said, where the reaction happens. The real cathode, the chemicals in the cathode is manganese. Okay, manganese. In this case, the charge of the manganese, let me ask you guys, what is the charge in this manganese? What do you think? Okay, you're not looking it up. Take a look at the formula. How do we figure out the charge? We studied that before, right? How do we figure out the charge for ionic compound? If we don't know the charge, how do we figure it out? We'll look at what? The nonmetals, right? What is the charge for oxygen?
2.
-2, right? But we have how many oxygen? 2. So the charge of manganese is
2.
Each oxygen is -2. 2 oxygen is -4. So manganese is what? +4 charge. Right? +4 charge. And after that, manganese becomes +3 charge. You see that 3? The subscript 3 come from what? From the charge. So 4 becomes 3. Gain how many electron? Gain 1. But you have 2 electron loss. That means you need how many substrate? You needed 2 of those. Do you see that? In order to gain 2 electron from zinc, you needed 2 of those. Okay, that's what happened at the cathode. Again, that's the chemical in cathode. The paste of, you see that, this reddish? The paste of manganese. Okay, but they're actually surrounding where? The graphite rod. That's the cathode where reaction happens. But the chemicals are the manganese oxide. Okay, oxide. And inside is a dry paste, again, of what? Of potassium hydroxide. Sometimes you see the leakage of a battery, right? When you put in there the battery or in a device, your flashlight, when you open it up, oh shoot, the battery leaked. You see the white pasty stuff? That's mostly potassium hydroxide. Okay, and if you add these two together, you get the overall reaction of alkaline battery. Okay, so this is what happened inside an alkaline battery. Okay, next, let's take a look at the nickel cadmium cell again, but now we're not showing the simplified reaction because what's really happening inside the nickel cadmium battery. Okay, cadmium again is the anode losing electron, and after losing electron, cadmium gain combined with 2 hydroxide to become cadmium hydroxide. Okay, this is what happened in the anode. The cathode is nickel oxide hydroxide. Again, gains 2 electrons to become nickel hydroxide, and add two reactions together, you get the overall reaction. Okay, actually, I think they forgot to put a 2 in front. There should be a 2 in front because you need 2 next one. Okay, they forgot there should be a 2 in front. Okay, let me change that. Go. Okay, then after you have these two reactions together, you'll get the overall reaction. Again, you can see that in overall reaction, we don't show what electrons, because the electrons are canceled on both left side of here. Now, this is a quick practice and also something to show you what's typical about a chemical reaction. No matter we're talking about half reaction or over reaction. Okay, we didn't emphasize that before, but if you look at these reactions, this is again the nickel cadmium cell, this is oxidation, the half reaction, this is reduction, half reaction, this is over reaction. If you check these three reactions, you will find out all these reactions are balanced. Okay, are balanced. They're not only balanced by the mass, they're also balanced by the charge. Okay, let's take a look. Question number 8. Is each equation balanced in terms of number of atoms? That is by the law of conservation of mass. Okay, take a look at these reactions. For example, the first one. 1 cadmium, what? 1 cadmium. 2 OH, what? 2 OH. The electrons doesn't have mass, so we don't have to worry about the mass of the electron. The same, the bottom one. 2 nickel, 2 nickel. 2 hydroxide, 2 hydroxide. 2 water, 2 oxygen. I'm sorry, 4 hydroxide. And if you add the hydrogen and oxygen, you will see they are all balanced as well. Okay, all balanced. And the same for overall, because you add these together, you get the overall. Okay, so again, no matter for oxidation or reduction or the overall reaction, in terms of the number of atoms, they're all actually what? Balanced. But what's more typical about a battery reaction is not only they're balanced by the number of atoms, they're also balanced by the electric charge on both sides. If you take a look at these reactions, for example, the top one, the oxidation one, what is the charge on the left side? 2 minus, is that right? What is the charge on the right side? 2 minus. Electrons don't have mass, but electron does have what? Charge. So you can see that the charge is also what? Balanced. The bottom one, the middle one, reduction. What's the charge on the left side? 2 minus. What's the charge on the right side? 2 minus as well. So again, these are still chemical reactions. That means their number of atoms and also the number of charges should always be balanced. And finally, a quick question, something we have mentioned before. How do you distinguish an overall cell equation from a half reaction? How do you tell? If I give you an equation, how do you know it is a half reaction versus an overall reaction like here?
If it has electrons.
If it has electrons. Half reaction will show up what? Electrons. Overall reaction what? It doesn't show, but electron is actually now transferred between these two substances. Okay, next. Okay. Nickel cadmium battery, okay, like the one we use in our power tools, you know, is rechargeable. Okay, rechargeable means the reactants can go to products through an electron what? Transfer. We call the process discharging when we use the battery. But the reaction is in fact reversible. So the products can be turned back to the reactants by what? By reverse the electron transfer. By applying what? External charge. And we call that process what? Recharging. Okay, this charge, this battery is rechargeable. And you might wonder, how do I know if a battery is rechargeable? What requirements must be satisfied in order for a battery to be rechargeable? Okay, these are the two most important, I put in red, requirements. If you need a rechargeable battery. One of the requirements is that both reactants and products must be solids. You can see that they're all solids inside a battery. And number two, the solid products must cling to a kind of like a grid, like a plate, something, instead of free dispersing inside the battery. Okay, they're not free, they're actually cling onto a what? Onto a plate, onto a grid. In order for a battery, again, these are requirements for battery to be rechargeable. Of course, when the voltage is applied to the grid, these products can be what? Can be converted back to where? To the reactants. So in order for a battery to be rechargeable, we have to satisfy these two requirements. Both solids, and also the solids must be clean to a stainless steel or some certain type of grid. Of course, eventually, the accumulation of impurities, breakdown of the separators, and also generating of some byproducts will eventually what? Shorten and eventually end its life of a rechargeable battery. It's not forever. Okay, you will have debris inside the battery and breakdown of the reactants and products. Eventually, the rechargeable battery life will be shorter and shorter, and eventually will be dead. All right, next. Okay, next. This is the battery in our car, the 12-volt lead acid battery. Okay, like I said, lead acid battery is rechargeable, and it consists of 6 lead acid cells wired together. Okay, there are 6 of them. That's why the volt is 12. Like I said, each volt is 2. And this is the overall reaction of a lead acid battery. As you can see, that the battery is very interesting. The anode is lead metal. The cathode is lead 4 oxide. Okay, 4 oxide. These two reactants are actually submerged in a solution of sulfuric acid. That's why the acid of sulfuric acid, people call it battery acid. Why battery? Because they're actually inside the car battery. Okay, a lot of people call the battery acid. Of course, both the reactants and products are cleaned onto the plate, okay, onto these metal plates. That's why the battery is rechargeable. Okay, the product, lead sulfate, is also a solid. Okay, lead sulfate. Let me ask you guys the charge again. Okay, we have studied these charges before. Sometimes you may realize, okay, the charge for metal is 0. But what about the charge for this one? I've done this many times. Lead oxide, what is the charge for this lead? What's the charge for this lead?
Would it be 4?
4, right? Plus 4 charge. What is the charge for this one? Lead sulfate. No? What's the charge for sulfate?
2.
Minus 2, right? So what's the charge for lead? Positive 2. Right?
Oh, I was just putting
Minus 2 and what? And positive 2.
Oh.
So you can see what happened is 0 becomes what? 2. 4 also what? Becomes 2. So you're transferring how many electrons? 2 electrons. This one loses electron becomes what? Positive 2. This one, positive 4, gains 2 electrons to become what? Positive 2. They both become the same thing. Right? 0 and 4 becomes what? Something in the middle. Okay, this is what's interesting about lead acid battery. They both become the same thing, lead sulfate, which again is a solid, also cleaned on the plate. Okay, on the plate. But again, the anode is lead. The cathode is lead oxide on this plate. Okay, lead oxide. And besides the car battery, okay, besides in our cars, lead acid battery is used in many places. Like these small vehicles, like small golf cars, shopping cars, or like this what's it called? forklift cars, and sometimes in the toy, the kids drive those small toy cars, are all powered by lead-acid batteries. Different voltages, of course. Our car is 12 volts. Okay, they're the power horse because what? They're so efficient and they're cheap. Okay, because you need them everywhere. Think about it. But one of the problem, of course, is what? Is the lead. Lead is a very heavy metal and highly toxic metal. Okay, that's why the recycling of this is essential. Okay, we have recycling battery program. Whenever you change battery, you never take it home, right? Wherever you buy the battery, they will take your old battery to what? To give you a discount. Otherwise, your battery is gonna be very expensive. Okay, the recycling is one of the issue for lead acid battery because lead is very, very toxic. Okay, the last one I want to introduce you here is the one that again used in our cell phones battery. It's called lithium-ion battery. Okay, lithium-ion battery is basically based on lithium. Okay, lithium. Later on, we're going to study why lithium batteries become more and more popular. Not only nowadays using our portable devices like cell phones, battery, iPads, they're actually used on vehicles. Okay, Tesla battery is lithium-ion battery or lithium polymer battery. Okay, we want to explain why lithium is so unique, but here is what happens in the lithium-ion battery. Okay, it is a network of lithium metal oxide and also lithium ion. What happened is lithium ions simply shuttle back and forth between these two electrodes. Okay, in the anode, lithium loses electron to become lithium ion. And then lithium ion goes to the cathode to gain the electron to become lithium metal again. Of course, it's in complex with cobalt oxide. Okay, it's in cobalt oxide. And lithium ion battery is also rechargeable, means they will go in backwards. Okay, they're built on the network of lithium oxide and lithium ions. Right? And when we study batteries, okay, after we see all those type of batteries, one thing we want to talk about is one of the uses or one of the future directions we want to use batteries in our what? Is in our cars. Okay, in our cars. Because this technology has been existing for more than what, 20 years, I would think. Okay, the first type of vehicle that uses battery is called hybrid electric vehicle. You guys know what is the most earliest model of hybrid vehicle? One of the earliest model of hybrid vehicle. It's everywhere.
Is it Prius?
Toyota Prius. What is a hybrid vehicle? It's a combination of what? Of gas and battery in a vehicle. Under highways, long distance, it uses what? Fuel. But in the short distance, like local and start, they use battery. Okay, they use battery. Okay, in a hybrid battery, there is a traction battery pack. So you can charge the battery when you are taking a break or when you have some frictions happening inside your vehicle. Okay, of course, you have to fuel the vehicle as well because mainly the vehicle is based on gasolines. Okay, this is the mileage. Okay, mileage of some hybrid vehicles. The liters for the 2019 model is shows here. Okay, you can see that these are the mileage for city versus highway. The reason they have high mileage is because what? Because in local and also in the first starting part of the vehicle, they use what? They use battery. They're not even using gasoline. That's why they have very high mileage. Okay, these are some of the models. Okay, Toyota Prius is one of the earliest ones. There's another type of hybrid vehicle. Like we said, Toyota Prius, you what? You're using frictions to power the battery, to charge the battery, so that it can use at low speed. But there's another type of hybrid vehicle is called a plug-in hybrid electric vehicle, PHEV. Plug-in means what? You can charge it you can charge it. So the battery in the plug-in inverter is chargeable through our power outlet. But because it's a hybrid, means what? It still uses what? Gasoline as well. The battery inside a plug-in battery, a plug-in hybrid electric vehicle is relatively small. In fact, I think last time I went to China, a lot of my friends, most of the people in China are nowadays using plug-in electric vehicle. They actually, for regular commute, okay, like daily commute, you can basically rely on the battery solely. You don't need to use gasoline. Only if you want to go outside, hey, I want to go long-term trip to a family or friends, you started using battery. I think that last time, again, it's a few years ago, the battery can last 50 miles. Okay, that means what? Regular commute is enough if you're in a city. So every day you go home and charge it 50 miles, but if you need more, you're now worried about the vehicle died on the road, you can still what? Start using gasoline inside because it's a hybrid, it's not EV. Okay, that's very popular nowadays, especially in China. In the United States, I don't know, these are the models for the top leaders for the models. Okay, BMW i3S, Toyota Prius Prime, Honda Clarity, on Ionic. You guys can search if you're interested. Okay, these are again, plug-in means what? You can charge the battery. You don't have to rely on like taking a break or something to charge the battery. You can charge it in home. But again, the battery is relatively small. It won't last long distance. Okay, if you have long distance, you still rely on what? Gasoline. Okay, gasoline. This is something I personally like a lot. Okay, like a lot. Short distance, I can save a lot of money, but long distance, I don't worry about that my cars die on the highway, right? Okay, and of course, another direction, like we said, it's still early stage, is full what? EV. EV stands for what? Electric vehicle. These vehicles don't have our traditional what? Internal combustion engine. They don't burn gasoline. They're totally what? Rely on a large battery. Okay, of course the most famous one is Tesla. Okay, Tesla's 3, Tesla S series, Tesla X series, they're all EVs. Of course, their mileage, of course, converted mileage, because they don't even burn gasoline. So their mileage per gallon is converted, like based on the charge of the cost of electricity. And it's super high, right? It's super high. Okay. This one I think is very famous, like a Chevrolet Bolt. It's tiny though. Okay, it's tiny. Okay, Honda, like a Hyundai Kona electric. And there's a new brand. It's the KN, right? Have you guys seen that KN model on the road? KN is from Kia, I think. They're also very popular for EV nowadays. And so this field is happening fast. Okay, this is from, of course, the chart from 2019. Okay, Bolt is small. I think Bolt can last maybe 200 miles or 100 miles. I'm not quite sure. Okay, but you can check their mileage range. Okay, and this chart shows you the increase of plug-in hybrid EV sales worldwide. Okay, the leading increase happening in Norway, Germany, and the United Kingdoms. Okay, European countries are actually boosting a lot on the hybrid vehicles and also EVs. Okay, EVs. And the greatest sale, of course, happened in China and Europe, but the increase happens in these three countries. Okay, it's based on also the economy and also the policies, local policies. Okay, I heard in China by 2014, I think, maybe they will postpone that, but a few years ago, there will be no gasoline-powered vehicles on road. That's policy, right? If it is policy, then it's enforced. United States, I don't know how many years they're going to take. There's based on a lot of infrastructures, such as charging stations, right? Chargers, the cost of the EVs. Okay, a lot of factors costing that, and also the lobby of these gas companies. So there's a lot of factors. It depends on from country to country, but I'm going to show you the trend. Okay, that's what happening across the world. European countries are actually enforcing that more and more maybe. Okay, and last part of today's part of this lecture, we want to briefly talk about the metals. If you guys think about all the batteries we have seen so far, alkaline battery, lithium-ion battery, lead-acid battery, they always use what? Metal. Okay, no matter lead, cadmium, lithium, manganese, zinc, they're all what? Metals. In order to realize battery, the metals is essential. So there are a lot of questions to be answered about the metals. Okay, these are some questions for you to think about. You can search the internet, or you can take a brief look today. For example, what types of battery are most commonly recycled? Okay, remember metals, when we use them, they will be what? They will be used. Okay, the metals, if you want to keep getting the metals, you either have to, like mining ore metals, or have to recycle them. So think about what type of batteries are recycled. Normally we recycle what? We recycle rechargeable batteries. Okay, recycle batteries. And why recycling nickel cadmium battery is more critical than recycling alkaline battery? It has to do with what? These two metals. They may be toxic, they may be expensive, and also some reasons why household batteries, like our dry batteries recycling program, are not effective. Again, it's related to what? To regulations, laws, and also recycling centers. I know a lot of counties even don't recycle batteries. Okay, so these are something you can search up and learn about those recycling programs. And next chart shows you the sustainability of energy storage devices, like the metals. Okay, some metals are having risk to supply. Some metals are rising threat from increasing use, and some metals are already serious threat in the next 100 years. You can see these metals. Okay, the chart is showing that metals. What metals are in heavy risk? Okay, what metals are rising threat and rather serious threat? Okay, these are some elements showing the endangered elements, especially what metals are endangered. And more questions. Okay, is when we talk about recycling metal, used metals, but is that really possible for a metal to become extinct? Okay, what does it mean extinction? When we use a metal, what does used metal become to, right? Is that like other living species, they extinct, but is that possible for metal to extinct? And also, which of the highlighted elements above are currently in demand for batteries? Are there any non-highlighted elements that are currently being used or tested for future use? Okay, these are something you can search the website, search it, and learn more resources to answer these questions. Think about the elements that are used or in high demand. Okay, and of course, among all these elements, like I said earlier, I want to briefly talk about the one we're actually using a lot nowadays, and also in increasing demands, that is the metal lithium. Because again, like I said, lithium is not only used in our portable devices, we're carrying lithium batteries everywhere. And also lithium batteries are increasingly used in what? In making hybrid vehicles and also electric vehicles. So what makes lithium important? What makes lithium special? And why, how do we answer these questions about lithium? Okay, why lithium? What lithiums are containing batteries are mainly used for? Like I said, portable device, cars, okay, laptops, cell phones. Okay, why lithium is unique? Because lithium is in group 1A. Then why group 1A metal will be ideal for making a battery? What makes group 1A metal ideal for battery making? And group 1A metal includes lithium, potassium, sodium, rubidium, these metals. But why lithium? The first one has the advantage of over other ones. And where can we apply lithium? Have you thought about that? Okay, these are some questions, but one question I want to ask you about you guys is, why do you think group 1A metal, which is lithium is one in group 1A, is very good for a battery? One reason, we have studied before. Think about it.
They have more opportunity to accept electrons.
Accept or
Give.
give electron. How many electrons? Lithium has how many valence electrons? Think about it. 1. Why? Because the group number is what? 1. These metals only have 1 electron. So that means these metals will what? Very easily to what? To give 1 electron. The losing of electron for these metals is easier than any other metals. That makes these metals ideal for what? For battery. Remember, battery metals are mostly what? At cathode. They lose the electron, they're being oxidized. And lithium is very actively being oxidized in a battery. Okay, next question, which is even more important. We know lithium is very ideal for battery, but why lithium is overrun all the other group 1 metals in making batteries? One of the reasons, and the most important reason, is lithium atoms are small and light. What does a small light tell you? Small light means what? When they're used for making batteries, they're what? They're lightweight, right? Remember, we need to carry those batteries. We need to put in battery in the car to drive, right? So we want the weight to be what? To be small. And lithium has that advantage of being lightweight. Okay, being light. This is a picture of lithium metal. Of course, because the lithium metal is too active, we store lithium in oil. You see that? Even storing oil, lithium metal is actually floating. What did I tell you? The density of lithium is what? It's very light. That's why you even float in oil. Okay, float in oil. Okay, and the third question is, where do we find metal? Lithium. Okay, lithium is actually far less abundant in the earth crust than sodium and potassium on the other ones. And they are mostly found in remote locations. Okay, remote in like salt lakes. Okay, this is one of the lake. Okay, here shows the picture of a lake. One of the world's largest lithium deposit is in a salt lake in the desert area of Chile. Okay, they're in the form of lithium chloride and lithium carbonate, in the form of those in the salt lakes. They're all soluble. Lithium salts are soluble, so they're dissolved in the salt lake. Sometimes they deposit on the surface. Okay, and this one shows you the called energy density. You can see this is where lithium batteries are located. Okay, lithium polymer, lithium ion battery, these are located. It shows these batteries not only have smaller weight, but also what? Smaller size. It tells you what? These batteries are very advantageous for what? For carrying with us in portable device, in vehicles, because not only we can create a battery in lightweight, but also create a battery in what? In small size. Compared to lithium ion battery, take a look where the lead acid battery is located. Here, means what? They're heavy, they're what? They're big. Okay, that's why you can see, have you guys tried to lift off the battery of the lead acid? It's very heavy. Okay, there's no way you can use lead acid battery in a computer device, right? Your computer is 3-4 pounds. That battery is more than 3-4 pounds. Okay, that's why some advantages of using lithium. That's why lithium metal is getting increasing demand because of these properties. Okay, and finally, you guys have heard of it. Okay, why? Heard of the lithium metal ion, especially batteries, Tesla, or a few years ago, Samsung Note 7, is that Samsung Galaxy 7 Note 7? They what? They catch fire. They explode, right? That's actually common for lithium ion batteries. Okay, not something new. That's some intrinsic property of these metals. Okay, because they are very what? They are very active. Okay, if you put lithium water, or sodium water, they will catch fire by itself. Okay, catch cells. But of course, in battery packs, these metals are actually sealed. Okay, sealed to prevent exposure to air, to water. But what happened is when the separator between the electrodes are broken, which will generate a short circuit and also some major heat, that will cause what? That will cause fire or explosion. Okay, a lot of car batteries, you guys heard of tons of news of Tesla catching fire, Tesla explosion, and also some cell phones. Okay, that's why a lot of regulations of mailing Lithium ion contains battery. You see a box, right? On the label on the box, if you buy an iPad from her, you will see that the box on the iPad shipping to you has a kind of lithium battery label that show that this is the battery inside. There's a potential of. Okay, a lot of companies do not allow lithium ion battery to be on board. Okay, to be like a checked in on board. You can carry a personal device. Okay, and also because of the property of it. Right? So this is a quick practice for you. You can do it at home. Kind of like a review the charges, review the terms of oxidation reduction, and who gains electron, who loses, and all leave it out to study this part, this practice. Okay, that's all for today's lecture. We talk about what is the battery, and what is the principle of battery, and how do the batteries we use daily, and how do they work, and also briefly talk about the metals that are involved in battery. Okay, tomorrow, or not tomorrow, Thursday, we're gonna discuss some future directions of battery. Okay, how do we use battery, and what are the future or newer fields of voltaic or galvanic cells? Right? Let me stop the recording.